go over all the different data analysis projects that you might be now addressing or try to get your teeth into. So essentially, we have all of these different data analysis projects, right? So we have, for example, stroke rehab, we have unresponsive wakefulness, and other DOC type pathologies, for example, locked inpatient data analysis. We have a P300 speller data analysis, SSVEP data analysis, ECoG hand poses data analysis. So this is in that case invasive data, right? And we also have ECoG video watching analysis, which is also invasive data from patients. I'm going to go kind of briefly through them. Again, if you then still have questions afterwards, for example, I will be in Discord and you can just ask me questions. That's what I'm here for. So please don't be shy. Just ask if you have any questions and we can then really get into these questions specifically. So this will just be a rough overview. So you have like kind of a general idea what these data are all about. And also don't worry, you will get a link to these data later on. So you can download them. And this will also be provided via the Discord. Right, so both me, so my name is Sebastian Siegerseitner, and my colleague Johannes Grünwald will be helping you with these data analysis projects if you have questions. Obviously, we will not be doing the work for you, but if you do have questions, we will be there to help you. So let's see. Next up, or first up actually, we have the stroke rehab data. And this you might already kind of know is from the recoveriX system. So the recoveriX system is used for stroke rehab, it's used for MS rehab as well, and is a BCI system which combines motor imagery, right? So the mental rehearsal of a movement, meaning you or the patient is imagining to perform a movement, and this is recorded via the EEG cap. This is the EEG cap right here. And the computer right here is analyzing the data, so the EEG. And if the patient in this case is like participating well, is concentrating, then FES, which is functional electrical stimulation. So you can think of it as simple muscle stimulation. You can see the two FES pads here, which are applied to the forearm muscle, are being activated, and this then actually leads to the hand movement, right? So the patient essentially is only imagining the movement, computer is detecting the movement, and then if the patient is participating properly, then the patient is receiving FES feedback. So this is this muscle feedback, as well as visual feedback by an avatar. The avatar you can't really see here, but there would be here a computer screen where you have the avatar feedback as well. So in general, what you will find in this file is something that looks kind of like this. So we have a trial-based data set, and each trial lasts 8 seconds, right? So at 0 seconds, there is the attention sound, essentially like a beep. And then 2 seconds after that, the patient is instructed to either perform a left hand or a right hand movement. And then the patient is doing that, meaning exactly at 2 seconds of each trial, the patient starts to imagine this movement and is doing so all the way until the end at 8 seconds, where then the patient is told to relax. The feedback phase, so this is essentially the phase during which then the FES could be enabled, starts at 3.5 seconds. So this is essentially kind of this trial structure. Right. To the data sets themselves, we have 3 subjects, P1, P2, and P3. And we have different stages. Stages, you can see here, little 1, essentially means pre is the first rehabilitation session and post is the last rehabilitation session. And of course, since this is a BCI application, we have training data and we have testing data. And these are in two .mat files. And you also have some reference accuracies, which you can try to get them better, or you can try your own approach, or you can analyze the data in a completely different way. So it doesn't have to be that you are like doing this typical train test approach, which one often does for BCI applications. But you can analyze the data however you want. Feel free to go wild on it. Yeah, so this is essentially what we have for all of the patients. And additionally, in each of these files, we have fs, which is the sampling rate in hertz, and we have a y, so this is the actual EEG data, which is structured in the number of samples times the number of channels, so it's a matrix, and we have the trigger, which is +1 for a left movement and -1 for a right hand movement, or a right hand imagination, actually. Yeah, if probably people will still ask, just in case already. Yes, sometimes the EEG data is kind of pre-filtered and sometimes it is more raw. So this depends on the data set, how it was recorded. Okay, to the data set again itself, we have, of course, a montage. And the montage you can see here. We have 16 channels. And you can see the channel labels, numbers here, labels here, as well as, of course, let's say a visual depiction of the montage. So all of the white channels here are the channels that were being used to record this data. This is the files. So we have dataset information, which kind of summarizes what I just spoke about. Then we have a publication for reference for this TVLDA approach classifier. We have the electrode montage, which I just showed you. We have an overview of the dataset, which I also just showed you. We have the datasets themselves, and we have another publication for reference. On to the next one. The P300 speller is already, I'm assuming, kind of known. If you are looking at something that is flashing, that is blinking, whatever it might be, then you're getting visual input. And this visual input elicits response, especially on the visual cortex. Pretty obvious. And if now there are many, many different things flashing, but you are only paying attention to, let's say, all of this row here, as you can see from the faces, they're like lighting up, but you're only concentrating on this one face and you're counting whenever this face appears. Then you are giving attention to the specific face. And what you will have is a P300 response or P3 response, which is essentially like this big bump here, roughly at 300 milliseconds after the stimulus. So here's the stimulus. This would be 100 milliseconds. This would be maybe 200 milliseconds. This would be roughly 300 milliseconds. So there's this big positive deflection. That's why it's called P positive, 300 for 300 milliseconds after the stimulus. Whereas for non-targets, so for all of these guys, you would not have this big positive deflection. And therefore, let's say, both you visually, but also the computer, much better than you, can differentiate between what you're currently focusing on, what you're looking at, and where your attention is drawn to. So in comparison to the previous data set, which was kind of band power based, this data set is event-related potential based. Data sets themselves again. We have in this case 5 subjects and some comment. So these were all wet recordings. What does that mean? Essentially, gel was used for these recordings and row column flashing was performed. And the accuracies you can see in the abstract, which is provided so in the reference publication that is provided. Again, variable description, sampling rate, EEG data, trigger. In this case, we have a little bit of a different montage, as you can see. So this montage is mostly focused on the visual cortex back here, but also the CSET and FSET channels are being used. Why are they being used? Because the P300 is especially focal for these CSET and FSET locations. In this case, as you can see, only 8 channels of data. We have the P300 speller files, electro montage, which I just showed you, dataset overview, P300 publication, another P300 application, and the datasets themselves. Steady state visual evoked potentials, that's the next dataset, or in short, SSVEP. What's that? So similar as we just spoke about when you're looking at something that is flashing, if that thing is flashing very often, so for example at 14 Hertz or at 17 Hertz, and you're focusing on them, and then if you perform a power spectral analysis, you will see that you even have a 17 Hertz peak in your EEG data or in your power spectrum, or a 14 Hertz peak. If you look at the 14 Hertz flashing light or object or whatever it might be. Just in case you don't know, Hertz means essentially that this thing, this object, this light is flashing 17 times or 14 times per second. So this is one other way that you can differentiate based on somebody's EEG activity on which thing, on which object they're currently focusing on. Regarding this dataset, we have stimulation frequencies of 9, 10, 12, and 15 Hertz. And this is detailed in the class info .m file. We have a sampling rate of 256 Hertz. And we have, in this case, 9 kind of channels. 2 to 9 are the EEG channels. So again, 8 EEG channels in total. Channel 1 is the sample time. So this is just a time vector, right? We have channel 10, which is the trigger info, whether the LED was on or off. And we have a channel 11, which is the like a reference LDA classification output. And we have 2 datasets from 2 subjects. Regarding the montage, here it is even more so, just based on the occipital lobe, so only on the visual cortex. Why? Because in this case, there's no real attention mechanism involved on that, no P300 that you might expect, because you cannot count or put attention to something that flickers at 14 Hertz. And it's only visual based. The SSVEP files, we have the class info file, we have the data description, SSV reference publication, electrode montage, which I already showed you. And we have all the different data sets. And in this case, we have them exported as .mat files and as EDF files. To the unresponsive wakefulness and locked-in syndrome patients or data sets. What does UWS mean? It means unresponsive wakefulness syndrome. And if you're really interested in like, okay, what is that and how can we help these kind of patients, there's a really good article on Frontiers for Young Minds. So this kind of breaks it down very simply, very easily to get a feel for what this whole thing means. I can share the link with you. Just message me on Discord or add me on Discord afterwards. I will introduce myself on Discord anyway to all of the data analysis groups. But yeah, regarding the data sets themselves, here we have a vibrotactile P300 paradigm. Vibrotactile means you kind of have like small little vibrators attached to your right wrist and to your left wrist and to your left ankle. So there's 3 vibrators in total attached to your body or to your extremities in this case. And again, depending on which kind of vibrator or stimulus you're focusing on, you will have again this P300 response. So previously, I spoke about this P300 response in terms of visually evoked potentials, but the same thing essentially applies also for somatosensory evoked potentials, meaning doesn't matter whether I'm looking at something that is, let's say, flashing and I'm focusing on it, or whether I'm concentrating on, let's say, my right hand, which is sometimes vibrating. Doesn't matter. In both cases, you will have a P300 response, which the computer can detect nicely. We have a montage, and in this case, we see that it's mostly over the sensory motor cortex with, again, this FZ and CZ electrode. And yeah, 8 channels, as you can see. And the data sets. We have data of 2 patients doing VT3, so this means vibrotactile 3 paradigm. So these are these 3 vibrators attached to the respective limbs. And we have 2 sessions, right? So we have P1, which is patient 1, and we have the first session, and we have the second session. And the same thing for P2, first session, second session. And you can see that depending on the session, the patient sometimes has either a very low accuracy or a greater accuracy. And this is very likely due to like patient variability. But nonetheless, you can try and improve, especially this low accuracy data set or classification if you want to. We have a sampling rate, again, in Hertz. We have the EEG data, and we have the trigger, which is -1 for the distractor. So the distractor is essentially this left ankle, which the subject should never pay attention to. +1 for the non-target. So this is either the left hand or the right hand, and +2 for the target, which they should be paying attention to. And just so you have an idea what this trigger data looks like in general, here's what it might look like. So this is time in seconds. And here you can see the 2, meaning this is a target. This would be a non-target, which the subject should be ignoring, as well as all of these distractors down there. So the distractors, as you can see, there are plentiful. Like they should all be ignored. They're just there to distract you. And these 2, you should only be paying attention to the 2, because the 2 is the target. Now to invasive data. And this is ECoG data and a person performing hand poses. Which kind of hand poses is the subject or the patient performing? So you can see here, this is a patient with implanted electrodes in a hospital setting. And the patient is, in this case, performing 3 different tasks. So essentially, you can think of it as rock, paper, scissors, or you can think of it as fist, a peace sign, and an open hand, right? So the fist would be the rock, the peace sign would be the scissors, and the open hand would be the paper. And this is, of course, randomized. So it's random which task appears after the other. And there's also a rest, which is, for example, 2 to 3 seconds. And then you have the instruction for the patient to perform the task itself for 2 seconds. What you can also see here, which I'll speak about later, as well again, is a data glove. It's essentially like a glove which kind of monitors what the actual hand is doing. So what do we have in this data set? Here you can see the electrode grid, how it is placed over the motor cortex. We have 60 channels. And you will also see this image in the reference publication, where we provided this as well. We have a sampling rate in this case, which is much higher than for typical EEG recordings at 1200 Hertz. We have, again, this time vector. We have 60 ECoG channels. So these are completely raw and DC coupled. So you will have to perform pre-processing on them for sure. And they're recorded over the right sensory motor cortex. We have channel 62, which is the paradigm info, which is either 0 for the relaxed state, 1 for the fist movement, 2 for the peace movement, and 3 for the open hand, or put differently, rock, scissor, and paper. And we then have 5 channels for the data glove. So this is the thumb all the way through the little finger. Each channel here has its own little value, essentially indicating when is the subject moving the little finger, the thumb, their index, the middle finger, the ring finger, right? And in the order from thumb to little. The files, we have a dataset description. We have the MATLAB file itself, so that this is the MATLAB data file in this case, and we have a reference publication as well. Now to the last dataset now, which is the ECoG video watching dataset. So this is, in that case, again, invasive data. And a patient in a hospital setting, in this case, was shown different, or was shown a video where different things appeared. So for example, a sheet of paper appeared with like numbers or digits on them, right? Or for example, a face was shown to that patient as well. Or era or kanji or other objects might have been shown to that patient. And you will only know which patient or like which object or which thing in the video is shown to the patient if you check the video. And in this case, you will have to annotate the video yourself. Yeah, there's a reference publication provided, which is real-time detection and discrimination of visual perception using ECoG signals. And that looks all very fancy. You will have to read the data or in this case, the publication for yourself. What you can already kind of see, so this is just a little bit of a hint for you guys, is that here in this figure, you can kind of see these electrodes, which seem to be important as they're kind of marked with this little star shape and with this little object shape here as well. So especially these kind of electrodes at the bottom of the head, kind of. So this is a special location that kind of discriminates between or is very active when we distinguish between different categories. Also giving away the name, it's the fusiform gyrus or the temporal lobe. So here you can see again, this is in this case the montage. So we have many, many different electrodes, as you can see here, from 1 to 160 channels. And here you can also see the numbers, which you will also have in the channel assignment and stuff. So you will also have this picture yourself. And yeah, especially these grids down here. These should be the ones which are very important for your analysis. But feel also free to analyze all of the EEG data or all of the ECoG data in this case yourself. You also have a photodiode feedback. So this will be explained in further detail in the dataset information PDF. You have a STIM code and you have a group ID. And the data in this case are not referenced yet. So you will again have to pre-process all of your data. And that's it for the data analysis projects. Again, I'm going to give you the links to these data sets now on Discord. And of course, if you have questions, feel free to reach out. That's what we're here for. And good luck.